Hello everyone, welcome to the video. Today I'll be going over how to determine the dominant form of a molecule at different pH values. This is the molecule we'll be working with today. As an example, it's an amino acid. And notice it has three different functional groups. You have the NH2 here, the carboxylic acid functional group right here, and this long side chain. Now for this problem we are given the pKa values, which makes our lives very easy. Now we'll be going over two methods in order to determine the dominant form. You can choose whatever makes more sense to you and stick with that. Now the best way is to do it one functional group at a time for the given pH. The first method I'll be teaching is the scale method or the line method. I don't think it has a name, but basically you create this line of pH values and it goes from 0 to 14 like pH does. And we're gonna just put our pK values for our three functional groups on this scale. So 2 can fall about here. We're just going to approximate this, it doesn't really matter. 9 and 10. Okay, now let's start with our first pH value, which is 1. And now let's say 1 falls right over here. Again, you don't have to be exact, it just matters which value it falls below and which value it falls above. So 1 is right here, which falls below all three of the pKa values. That means in this, imagine a jar, a beaker with the solution. That means in this pKa there are many hydrogens, many hydrogens in the surrounding in the system. This means that because there's already so many hydrogens in the surrounding, all of these functional groups have no reason to lose their hydrogens. They will not be contributing anything special to the solution because the solution already has so many hydrogens. Therefore, when the pH falls below all of the falls below the pKa value, the molecule or the functional group will retain its H and exist in its acidic form. Therefore, at pH 1, where the pH is below all three of the pKa values, all three of the functional groups will retain their H's. So the molecule will look something like, so our carboxylic group still has its hydrogen. Our amine group still has, our amine group becomes protonated, because of the extra hydrogens. Same with this. So I feel like I didn't explain this too well so the reason our two bases gain the hydrogen is again the same concept actually, because there's so many hydrogens in the surroundings. It's more beneficial if these bases accept the protons. Let's go on and hopefully the next example will make more sense. Now at pH 2, notice how this falls right on top of the pKa of the carboxylic acid, but below the pKa of both of our bases and side chain values. So now what this means, when the pKa is exactly equal to the pH, that means it's a 50-50% chance. Half of the concentration of this molecule regarding the carboxylic acid will still have its hydrogen, and the other half will lose its hydrogen. And if you think about it, this makes sense because the pKa is equal to the pH, which means there's not too many hydrogens in its surrounding and not too less. That means the molecule has a 50-50 chance of either giving it away or not giving it away. So again, our molecule, you'll have to draw two molecules for this pH, just because you have to demonstrate that it doesn't just exist in one form, but exists in both equally. And if you don't draw both, it's like saying to the grader that the grader doesn't know if you know that it exists in both. So the grader might think, well, this person doesn't know that in this pH both of them existed in equal amount, and so you will not get the marks for it, and we don't want that. So notice our side chain and the amine group both are protonated. They have the extra hydrogen, and this is just because the pH falls below the 2 pKa values. But the difference comes when we're looking at our carboxylic group. In this one, it's lost its hydrogen. In this one, it still has its hydrogen. Okay, let's pick another. Let's say, actually, let's go with 5. Now, notice the 5 is above the 2 and the pKa of the carboxylic acid, but it's below both the pKa's of the side chains and the amine group. Now, again, if we go back to our example that this molecule is like in a beaker, that means there's enough hydrogens in the beaker to for these two groups to accept the hydrogen, but there's not enough hydrogens in the group that this the carboxylic part would need to keep its hydrogen. So let's draw this out. That means at a pKa of 2 and a pH of 5, the carboxylic acid has no reason to keep its hydrogen. Therefore, it just gives it away for in order to add hydrogens into the solution and make the whole system happier. But on the other hand, our pKa 10 for the side chain and pKa 9 for the amine group, they both fall above, and therefore they'll accept a hydrogen from all the hydrogens in the surrounding. They'll just take one hydrogen each to accommodate that, and the molecule at a pH 5 will exist in this form. Now let's do one last one. Let's get rid of all of this. Let's get one last one with this method, and then we'll move on to the second method. So now we have our pH 11. Notice how it falls above all of the pKa values. This means that in our little beaker, there's like a lack of hydrogen molecules. That means there's not a lot of hydrogen molecules, and therefore, at this pH value, all three of the functional groups will lose a hydrogen or will not be protonated. In the sense, they will be in their basic form. So what that molecule looks like, so our side chain, so our side chain right here will not be protonated and therefore not accept. Okay, let me just draw this molecule nicer over here. Okay, so starting with over here, our side chain will only have 2 hydrogens and 1 nitrogen. So in other words, it will not be protonated. It will not accept protons or hydrogens from its environment. Same thing with this amine group. This functional group will only have 2 hydrogens and will not accept the hydrogens from the environment. And as for the carboxylic group, which is acidic in nature, it will lose its hydrogen and therefore contributing it to the environment. If you think about this logically, it sort of makes sense because there's not a lot of hydrogens in the solution or in the beaker. This group is able to give a hydrogen away in order to add to the solution. These two will not accept hydrogens in order to maintain the hydrogen concentration in the solution. So therefore, they're all helping to keep the hydrogen they're all reacting in a similar way in order to respond to the amount of hydrogens in the solution. So now I'm just gonna copy this molecule right here and I'll show you how to use the second method. The second method is using the formula Ka over the hydrogen is equal to A minus, concentration of A minus, over the concentration of acid. Now this is derived from, if you products over reactants. And in a way, this is saying the same thing as our other line method, saying that when you have this reaction over here, depending on the pKa and its pH value, so depending on what the surrounding is like, the sorry, I forgot the word for it. The extent of dissociation will vary. If you have a low pH and there's a lot of hydrogens already in the environment, well, you're not going to go forward and you're not going to produce more hydrogens. You're going to stay over here and you're going to have more reactants. And that means that the Ka over the hydrogen concentration will be below 1. That means it'll be very small, like 0.01 or all those values. On the other hand, if in our little solution we don't have a lot of hydrogens, well, then the reaction will go forward. Oh my god. Come on. Okay, we'll go forward and therefore producing more hydrogens. It's all about balance and equilibrium. So now let's find out. Let's just do a couple of examples. So let's say at pH 1, which we've done already, but let's do it by this method. You'll have to do this for each functional group again to determine if its dominant form is A minus, which is the acidic form, or if it's still basic form, or if it still retains its proton, which is acidic form. So notice, in order for this to be dominant, the Ka over H plus concentration must be greater than 1, and in order for this to be dominant, the Ka over hydrogen plus must be below 1. Now for pH 1, that means, oh god, I don't have a calculator. Okay, so the pH, it's the negative log of H plus. So in order to determine H plus, we'll put in our 1 here, negative log, and so that's what you have. And then as for the Ka, let's start with our carboxylic acid, which has a pK of 2. Again, so the negative pKa is the negative log of Ka. So in order to determine that, you have 2 is equal to negative log Ka. 10 over negative 2 is your Ka, and therefore our ratio Ka over concentration of H plus becomes 10 to the negative 2 over 10 to the negative 1, which by exponents means minus negative 1, which means 10 to the negative 1, which is less than 1, and therefore it exists in its H minus A form, which means it's still going to have its hydrogen, and therefore the carboxylic group will still retain its hydrogen like it has in this form. Now, wow, I wrote really big. Let's move on to the second one. The pKa, or actually, let's go back to that page and just erase so we can still see our molecule. Let's keep that here. Sorry for the housekeeping. But let's just make note of our molecule in this pH. pH equals to 1. That this part of the chain, the carboxylic functional group, will still have its hydrogen because of what we found out earlier. Now next, the Ka and H plus of, let's go with this group. Now the pKa is 9, so it'll be 10 to the negative 9. Yes. And the pH is still 10 to the negative 1. And so we get 10 to the negative 9 minus negative 1, which is 10 to the negative 8. And so oh, that's still less than 1, which means it'll be in its acidic form, and that means it will accept a hydrogen and become protonated. Now, oh shoot, how many do we have? Okay, 1, 2, 3, 4. And for our last one, the Ka over hydrogen plus, the pKa is 10, which makes this 10 to the negative 10, and the hydrogen concentration is still 10 to the negative 1, and therefore the ratio becomes 10 to the negative 9, which is less than 1, and again this will also retain its acidic form. So this as well will become protonated, and if you compare this to what we had right here, you'll notice it's the exact same answer. Now let's work with pH 11 with this example just to really cover all our bases. Okay, so now at pH 11, let's again start with our carboxylic group. Our formula that we're trying to find out is this. So now our Ka, which is 10 to the negative pKa, and our hydrogen, which is negative. Okay, so let's just insert in our values. 10 to the negative 2, and then we have 10 to the negative 11, which means 10 to the negative 2 minus negative 11. Exponent rules gives you 10 to the negative 10 to the 9th, which is greater than 1, which means at a pH of 11, this the dominant form will be A minus, therefore the carboxylic component will have a negative charge and lose its hydrogen. Going to the next functional group, over here, so the pKa is 10 to the negative 9, and the pH is still 10 to the negative 11, just making sure that's what I have. So you'll get 10 to the 2, which is greater than 1, and therefore, okay, those are 2 bonds. This will not be protonated and remain as that, because this is also in its basic form. Last but not least, the pKa of 10 for our side chain. (10 to the negative 10 and 10 to the negative 11 equals 10 to the 1, which is greater than 1. And similarly, the dominant form will be basic. And so, like our other functional groups, this one will not gain hydrogen and therefore will not be protonated. And this will be our molecule at pH 11. Now let's compare and see what we had from the other method. And ta-da! It's exactly the same. So rewatch, or if you think if things are still confusing, rewatch whichever method made more sense to you, and really try to just go with that and try to think of it like what would happen if you had a beaker of this solution. If you had a certain amount of hydrogens associated corresponding to the pH level, if your functional group will feel the need to help the system by getting rid of a hydrogen or not accepting a hydrogen, or help the system because there's too many hydrogens by accepting a hydrogen or not losing its hydrogen. So I hope that made sense, and practice makes perfect. If you have any questions, please comment below and I'll try to get back to you. Thank you so much for watching.